Hello, and we're going to be talking today about the polar and nonpolar molecules POGIL. This is probably one of the POGILs that's going to take us a lot of time. So I understand if you don't finish it during the period, but I wish you lots of luck. So if you look at the first couple sections, you have up until, it looks like, problem number 10. So you're going to do the first 9, then you're going to hit the stop sign, then come back to this video and see how you did. Okay, so you should have done problems 1 through 9, and we're looking at, so let's start with problem 1. Model 1. Consider Model 1, how is a polar bond differentiated from a non-polar bond? And if you look in the top right, it looks like a polar bond is between, I will attempt to draw this, ball and stick, and one of them is darkly shaded, and one of them is completely white. Alright, and then it looks like a non-polar bond. So this is polar. I'll just put P for polar. The non-polar bond, one side, and they write the right side, but it doesn't matter, is darkly shaded, and one side is slightly shaded. So that's how they've drawn their polar bonds and their non-polar bonds. Alright, formaldehyde. This is number 2. Formaldehyde has a chemical formula CH2O and is trigonal planar. We learned about that yesterday. Draw this molecule using open and shaded circles as it might be shown in Model 1. Okay. So in order to be, so let's draw it first as a ball and stick model, or as a Lewis structure. We know it's trigonal planar. Looks like this. Polarity is a function of electronegativity. Okay? So two guys who are really different in terms of electronegativity are going to be more polar, and two guys who are really close in electronegativity are not going to be polar. So oxygen, really strong dude. He's going to pull hard. That'll make a polar bond, because carbon is not as strong. But carbon and hydrogen are pretty close in electronegativity, so their difference is not that big. We'll call that more of a nonpolar bond. And so when we draw this, I'll draw carbon as the central atom. I'll make him dark. When we attach him to oxygen, polar bond, bright white. When we attach him to hydrogen, partially shaded. Okay? That's going to be our excuse me. That's going to be our model for formaldehyde. Number 3. Label each diagram with the 3-dimensional shape that it represents. So this will be fun because some of the ones in the diagram didn't show up yesterday. So I'll start with the ones that we did see yesterday. And I want you to notice that whether they had polar bonds or not. So if you look at the left side and then you look again at the right side, the shapes are the same. They just, some of them have polar bonds or drawn with polar bonds and some of them aren't. Alright, so for number 3, we have this one. And that was trigonal planar. We have this one. It's a line or it's linear. We have this one. And it had the wedges. Remember, this wedge is coming out, and this wedge is going in. And we called that one a tetrahedron, or it's tetrahedral. We have this one. So those are all the ones we remember from yesterday. Oh, I lied. There are some on the right that are different than are on the left. Okay. So all this is going to start to look different. I'll use one of the ones from yesterday. We definitely had this yesterday. With the 2 lone pairs, which was bent. And we had this one yesterday, which was here, and then the wedge, and the reverse wedge, and the lone pairs, and this was pyramidal, because it was a pyramid. Okay, so that looks like all the stuff that we saw yesterday. Okay, let's do some of the new ones. Here's a fun one. We have up and down, and then we have the wedges going back, and then the wedges coming out. This one is octahedral. I like that one. Let's see what else we got here. Oh, we got this guy. Central atom, we have wedges in the back and in the front. I'm so good at drawing. But he's got lone pairs on top and bottom. This one is square, planar. Here, we have this guy, which we sort of had a version of yesterday. And he had lone pair here, lone pair here, lone pair here along the equator. This is still a linear molecule, believe it or not. It is exactly the same as this linear molecule that we drew up here. It just has more lone pairs that help keep it linear. So it turns out lone pairs don't contribute to what we call the shape. They just make the shape happen. Okay, got some more fun ones. Here's one. It's got the wedges coming out, and then a lone pair on the bottom. Okay, that would be a square pyramid or square pyramidal, because it has a square base instead of a triangle base. So this is a square pyramidal. If we go back up to this one, the pyramid from before that just said pyramidal, because this is a 3-membered base, we might call this a trigonal pyramidal. That actual terminology is used quite often. And after the square pyramidal, I only see one other that I can tell. And it's got this guy here. It's got a wedge on this side and a wedge on there, but a straight one on there. And up and a down. This is a trigonal bipyramid, or it's bipyramidal. It's got a pyramid on top and a pyramid on bottom. A lot of shapes. And I definitely lied earlier, or I wasn't paying attention, because there are some nonpolar molecules that have shapes that we don't see on the polar side, and some polar ones we don't see on the nonpolar side. So ignore me. Alright, coming down to number 4. We just put out all the shapes. Number 4. According to Model 1, can the shape of a molecule explain polarity? Justify my reasoning. Alright, let's go through some shapes. Let's go up here to the linear one. Well, if I look in my examples, I see a linear molecule on the left. At the top there's a nonpolar linear molecule, and on the right I also see a linear molecule. Those are both linear. If I look on the left and the right, I see tetrahedral in both places. Okay, I see trigonal planar. in both places. Do I see a trigonal pyramidal? No, I don't. But I definitely see tetrahedral both times. And I see a trigonal bipyramidal. Right there. I see that in both places. I see octahedral both places. So there are plenty of shapes that could result in a polar molecule, and plenty, but those same shapes could also result in a non-polar molecule. So according to number 4 and according to my model, can the shape of the molecule explain polarity? Maybe it can explain it, but it certainly can't dictate it. It can't. It's never like this shape is always. Well, I won't say never. There are some shapes that are always going to be polar or non-polar. No, I think they're not always non-polar, but there are some shapes that will always be polar, so I can't use it to distinguish. So I'll say not always. Let's go to number 5. Circle the correct word to complete each sentence. Nonpolar molecules never may always contain polar bonds. If I look at my nonpolar molecules, the trigonal planar one only has nonpolar bonds. The linear molecule in the top right of the nonpolar section only has polar bonds. That's interesting. Although the linear molecule in the bottom left only has nonpolar bonds. But the trigonal bipyramid at the bottom, that has a mixture of both. Okay? So in number 5, I think I have to use the word may. Because I've seen examples of all of them. Nonpolar molecules may contain polar bonds. That's 5A. 5B, polar molecules never may always contain polar bonds. So let's go up there. I look at the trigonal planar. The top left in the polar section has a couple nonpolar bonds and has one polar bond. I look at the linear molecule, polar, nonpolar. I look at the tetrahedral molecule, 2 nonpolar, 2 polar. The octahedral molecule, 4 nonpolar, 2 polar. I look at the bent molecule. Looks like all nonpolar. So all of these guys seem to have at least one nonpolar bond, at least in this model. But some of them don't have polar bonds. So if I go down to number 5, where it says polar molecules sometimes never may always contain polar bonds, it looks like they may contain polar bonds. Because not all of the things in that model contained polar bonds. All right, number 6. Student states that polar molecules are just molecules that contain polar bonds. It's true. If you're a polar molecule, you probably do have a polar bond. I realize that the bent molecule and the square planar molecule in the model had nonpolar bonds. I kind of disagree with that. I really think that the correct answer for B, even though it says may, I really think always is a more accurate description. So going on to number 6, polar molecules contain polar bonds. If there are no polar bonds, then the molecule is nonpolar. Do you agree or disagree? Okay, for number 6. So now we have to say if it has polar bonds, it can't be nonpolar. So let's go up there. Well, I look in the model 1 on the left, and I see the linear molecule had 2 polar bonds right there, plain as day. The tetrahedral molecule had 4 polar bonds, had a ton of them. So there are definitely molecules in the model that were nonpolar molecules, but that still contained 1 or more polar bonds. So I'm going to say disagree. And I will cite as my examples, example tetrahedron. The tetrahedral molecule had 4 polar bonds. Refuted. Number 7. How is a lone pair of electrons illustrated in Model 1? It is illustrated like this, 2 dots. That we should remember from yesterday. Number 8. Refer to Model 1. Circle the correct word to complete the sentence. Nonpolar molecules never, may, always contain lone pairs. Okay? In the nonpolar section, 2 of the molecules had lone pairs, all the rest didn't. So, looks like that's a may. They may contain lone pairs. And then part B, polar molecules, same question. Do they contain lone pairs? And if I look at the polar section, there are 3 that have lone pairs and the rest don't, so that's a may. Okay. Number 9, is the presence or absence of a lone pair of electrons sufficient to explain the polarity of molecules? Justify your reasoning. Let me make sure there aren't any. Yeah, no, it doesn't seem like that's the case. Well, no. We had some of each in polar and we had some of each in nonpolar, so it doesn't look like just the presence or absence is enough to dictate whether the molecule is polar or not. And I realized I wrote 9 and it doesn't look like a 9. But my eraser tool probably won't work for this. Okay. Cool. That's our stop sign. So now, you're going to go on to number 10, and you're going to finish just before number 19. So 10 through 19 is your next section. Attempt that, and then come back here if you get stuck or if you finish that section. All right, when polar bonds are present in a nonpolar molecule, how are they arranged around the center atom, on the same side or on opposite sides of the molecule? So I'm looking at the nonpolar section, and I'm looking for anything with a bond that looks like a white bond. So I'll draw some. So I'm going to find, the first one that I see is the linear one. Here's the linear one. And they drew it like this. Okay? So here's the central atom. And both of those bonds, since they drew them clear, or white, are polar. Okay? Then I will look at the octahedral just below it. The octahedral molecule looks like this. And we have that one, that wedge, that wedge, that wedge. And the way they've drawn it is like this. Nonpolar bonds around the equator, polar bonds at the poles, the North and South Pole. So in both of those cases, it looks as if the polar bonds are as far apart from each other as they can get. They're on opposite sides of the molecule. And you can say the same for the tetrahedral and the Trigonal Bipyramidal, which are also had polar bonds in the nonpolar section. So the molecules overall are nonpolar, but those polar bonds look like they're on the opposite sides of the molecule. So not on the same side, we'll say opposite. Alright, that's 10. Going on to 11. 11's, oh, excuse me, that was 10A. Missing it. Okay, B, when polar bonds are present in a polar molecule, how are they arranged? At the same side or on opposite sides? So going up to, let's pick the octahedral molecule. I think we'll get the most out of this one. So in the polar section, if you look at the octahedral molecule, it looks like this, up, down, and then the wedges, going back, going forward. Here we are. And the shaded ones are these guys. And if you look at the white ones, which are the polar bonds, they are here and here, which is on the same side of the molecule relative to everybody else. They look pretty close together. say in a polar molecule, they look like they're on the same side, which is much different than how they were arranged in the nonpolar molecule. And if you look through the rest of the polar molecules, all the polar bonds that you see are on the same side. All right, now we can go into 11. So 11. When lone pairs of electrons are present in a nonpolar molecule, how are they arranged? Same side or opposite? The only two I see are the square planar and the linear. So I see a square planar like this, wedges, 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 wedges. I'm not going to draw the circles in because all they care about are the lone pairs. Lone pair, top, bottom, opposite sides. When I do the linear one on the bottom left, lone pair, lone pair, lone pair, those are all 60 degrees from each other. Excuse me, those are all 120 degrees from each other, like an equilateral triangle. Again, as far apart as they can get. They're not on the same side, they're on opposite sides. So we'll say those are opposite. Lone pairs in a nonpolar molecule. And of course they're going to ask, what about lone pairs in a polar molecule? For B, so this was A, here's B. And if you look in the polar molecules, the three that have lone pairs, like the bent one is the most obvious because it actually has more than one pair. But the bent molecule looks like this, and here's the lone pairs. And lo and behold, the lone pairs are on the same side. So we see the exact same trend as we did up here with polar bonds. If you're in a nonpolar molecule, the polar bonds are opposite. If you're in a polar molecule, they're on the same side. If you're looking at lone pairs in a nonpolar molecule, they're opposite. In a polar molecule, they're on the same side. Okay. Those are good things to know. Number 12, consider the term symmetry as we use it in English and rank the following shapes from most symmetric to least symmetric. So when I think of a shape, I'll use a heart because it's my favorite shape. Because love. So here's a heart. And assuming I was a good artist, this is a symmetric shape if I can draw a line through it like a mirror, like both sides would be mirrored. And sure enough, my heart is symmetrical about that line. Again, pretend I drew it really well. That's a line of symmetry. So the most symmetrical shape should have the most lines of symmetry, the most planes, because I can't draw a line this way. That is not symmetrical anymore. The first line was, the second wasn't. Alright, so let's get rid of that. And let's draw some shapes. And let's see if we have lines of symmetry. And I've got these four shapes. Triangle, circle, square, and rhombus. Actually, I think it's a parallelogram. Not quite a rhombus. Just see if I can draw a better rhombus here. Or parallelogram. So with the triangle, it's not an equilateral triangle the way they drew it. So I don't have more than one plane of symmetry. I just have the one. If it was, I could have drawn two more from each of the other vertices, but I can't. With the circle, I have infinite. This is it, this is it, this is it, this is it. I can keep drawing anything that passes through the origin. Any diameters, I should say, are going to be symmetrical. So the circle should be the one that has the most symmetrical lines. With the square here, I have a line of symmetry this way, a line of symmetry this way, and that way, assuming I drew through the corner. So all four of those are symmetrical. 4 lines of symmetry. With the parallelogram, the corner lines are symmetrical, but not the verticals. I don't have symmetry about a vertical axis, and I don't have symmetry across a horizontal axis, so I only have 2 lines there. So if I'm ranking, there was 1 here, 2 here, 4 here, and infinity here. So the circle is clearly the most symmetrical, according to my definition of the term symmetry, and the triangle is the least. Okay. Now it says 13. Which set in Model 1, the nonpolar or the polar, contains molecules that are symmetrical about multiple planes? Alright, well, let's pick some. Let's pick... Oh, gosh. We could do... Let's do the trigonal planar, because that appears on both sides. So I have the trigonal planar, like this. Remember, he's shaded here, but no. Oh, on the left side, excuse me, the nonpolar version is shaded everywhere, but on the polar side, he's only shaded here and here. So if I want to draw symmetry for the nonpolar molecule, I can draw a line there, that's symmetrical. I can draw a line there, that's symmetrical. I can draw a line there, that's symmetrical. But on the nonpolar side, I can only draw one. That's symmetrical. But it's not symmetrical the other ways because I have a polar bond that's going to be different from those nonpolar bonds. So the nonpolar dude has 3 lines of symmetry and the polar dude only has 1. So to answer that question 13, which set, nonpolar or polar, contains molecules that are symmetrical about multiple planes? Looks like the nonpolar versions are symmetrical about multiple planes. And the polar version is only one direction of symmetry, if any. Okay? Good to know. Read this. Polar molecules have an unequal distribution of charge around the molecule as a whole. This could be due to a bond being polar or a lone pair being present. So read through that. So we're going to go on down to 14. 14 says, suppose a molecule contained 2 bonds around the center atom, and both those bonds were polar. What would the angle between those 2 bonds need to be for the molecule to be considered non-polar? Well, in order for them to be non-polar, the molecule has to be symmetrical about those 2 bonds. So we have a central molecule and 2 bonds. Here's one, and it's polar. So color this dude in. In order for this to be symmetrical, I have to draw the other bond exactly mirroring the first one. So that angle has to be 180 degrees. And we're also assuming no lone pairs. Because if there were some lone pairs, they could push that bond angle around. So this is a linear molecule, would be nonpolar in that situation. Number 15, suppose a molecule contained 4 identical bonds around the center atom, and all 4 of those bonds were polar. What would the angle between any of the 4 bonds need to be for the molecule to be considered nonpolar? Assume no lone pairs. Well, again, they would have to be completely symmetrical. And a molecule with 4 bonds that is completely symmetrical looks like this one, with the wedge and the reverse wedge. And that molecule is tetrahedral. But they didn't ask what it was called, they asked what's the bond angle. If you remember from yesterday, a tetrahedral molecule has 109.5 for all of its angles. So all those molecules are identical, or all those angles are identical. Okay. Again, no lone pairs. 16. If a molecule contains only one polar bond and no lone pairs, is there an arrangement that will make that molecule nonpolar? Justify. Only one polar bond and no lone pairs. So here's my molecule, and here's my polar bond. In order for this thing to be non-polar, there has to be, so the reason it's polar is because this guy's being pulled. This central atom is either really strong or really weak, and this outside atom is the opposite. So a polar bond is a relatively weak guy with a relatively strong guy. They're just both non-metals. So as long as these guys are both non-metals, and one of them stronger than the other, you've got a polar bond. But if all the rest of the bonds, and I'll just draw a bunch, I don't know how many there are, because this is a fictitious molecule, But if all the rest of the bonds are weak, they're not going to cancel out that polar guy pulling upwards. It's like a tug-of-war. You're non-polar if no one wins the tug-of-war. But if you've only got a polar dude in one direction, he's always going to win the tug-of-war because he's strong and everybody else is not. So I'm going to say no. There is no way to have an arrangement that would make it non-polar. You got to have symmetry. Okay, 17. We're filling stuff in. Okay. Well, they want us to draw some molecules. Dichloromethane, carbon dioxide, and ammonia. I'm not going to draw them out. Well, am I? Yes, I am. I'm kidding. I'm going to draw them. Chlorine, hydrogen, wedge hydrogen, backwards wedge, chlorine. Alright, does the molecule have polar bonds? It sure does. That comes from having a strong atom with a weak atom. Carbon's kind of in the middle. He's kind of neutral. He's not really strong or really weak. Hydrogen's kind of like carbon. Chlorine's really strong. So that's going to be a polar bond between the chlorine and the carbon. Chlorine strong, carbon meh. So yes, the chlorine bonds are polar. Polar. Hydrogens were nonpolar. Does the molecule have lone pairs? No. If there are polar bonds and or lone pairs, are they symmetric? Well, no lone pairs. There are polar bonds here and here, but they're not symmetric. They're not on opposite sides of the atom. So is the molecule polar or nonpolar? It is polar. Dichloromethane, a very polar solvent. Very famous solvent. Carbon dioxide. Does this contain polar bonds? You betcha. Oxygen is probably about as strong as chlorine, if not stronger. Pulls really hard on that carbon. So an oxygen-carbon bond is very polar. Does the molecule have lone pairs on the carbon? Nope. If there are polar bonds, are they symmetrical? Yeah, in this case they are. They are on exact opposite sides. So again, this is a tug-of-war between twins. One oxygen pulls to the right, one pulls to the left. So this will be not, this total molecule will be nonpolar because it's symmetrical. And the right side oxygen does not pull harder than the left side oxygen. So that tug-of-war, no one wins. Alright, and then we have ammonia. Hydrogen, wedge hydrogen, reverse wedge hydrogen. Remember, this wedge coming out at us, this wedge going back into the paper. Or the phone, or whatever you're looking at this on. Does the molecule have polar bonds? No, these are nonpolar bonds. Hydrogen is weaker, nitrogen is kind of weaker. That's it, kind of weakly polar, but normally a nitrogen-hydrogen bond is not considered very polar. And so let's keep going. Does the molecule have lone pairs? It does have a lone pair right there. If there are polar bonds and or lone pairs, are they symmetric? No, that lone pair is only going one direction. There's no lone pair on the other side to balance it. So this will be a polar molecule, even without polar bonds. Although kind of a weakly polar molecule. I think most nitrogen, most ammonias are considered fairly nonpolar. You got to pull harder than hydrogen and nitrogen if you want to make a dipole. I mean, it's going to have a dipole moment. It's just going to be very small. All right, 18. Draw the three-dimensional structure for each molecule, fill in the table to determine if the molecule is polar or nonpolar. Okay, we just did this, but but they gave us the structure. Now we have to draw it. So methane, you should have drawn this. Hydrogen, hydrogen, outwards wedge hydrogen, backwards wedge hydrogen. That is methane. Does it have polar bonds? No. Carbon-hydrogen is very nonpolar. Does the molecule have lone pairs? No. Are the polar bonds or the lone pairs symmetric? Yes, everything here is symmetrical. Is the molecule polar or nonpolar? Very nonpolar. Methane is the poster child for non-polarity, we'll say. Very oily molecule. Formaldehyde, CH2O, you should have this, oxygen, hydrogen, hydrogen. No wedge is needed because there are only 3 pieces here and there's no lone pairs to push them out of the way. So this will be trigonal planar. Oh, did I not mark that on the other one? I did not. This is a tetrahedron, this carbon. Tetrahedral. This carbon hydrogen. This methane. This is a trigonal planar. Alright, does the molecule have polar bonds? Yes, polar. We'll call that oxygen bond a very polar bond. Does it have lone pairs on the central atom, the carbon? No lone pairs. No lone pairs. If there are polar bonds, are they symmetric? This guy? No. This polar bond is not symmetric. It's only on one side. So is the molecule polar or nonpolar? This is a very polar molecule. Okay. And lastly, Xenon Tetrafluoride. This one's tricky because it's got an expanded octet. Xenon already has 8 electrons. Right? So the only way for fluorine to come and attack it is for fluorine to pull its electrons into a higher orbital. So what happens is each fluorine is going to pick an electron, grab it. But notice there are 1, 2, 3, 4 electrons that would be able to bond with a fluorine, more or less, if the fluorine was strong enough to pull it out of its orbital, leaving 2 lone pairs left. So when xenon difluoride or tetrafluoride happens, it happens like this. And lone pairs take up extra space, so we'll put the lone pairs on the vertical axis, and then we'll do wedges for the fluorines. So xenon tetrafluoride goes like this. Wedges, back wedges in the back, forward wedges in the front. So top and bottom, lone pairs, and then you can picture this is like a 90-degree here between that fluorine and that fluorine all the way around. So picture a square around the hemisphere, around the equator, full of fluorines. They're all orbiting the equator of this molecule. So this is square planar. Does the molecule have polar bonds? It doesn't get much more polar than a fluorine. Although xenon is a noble gas and would have it would pull back fairly hard. But it's a big noble gas. So we'll call this a polar bond. Does the molecule have lone pairs? It sure does. There's some lone pairs. Are they symmetric? In this molecule, even though there's a lot of polar bonds and lone pairs, the lone pairs are symmetric with each other, and the polar bonds are symmetric with each other. So everything is symmetric. So this will be a non-polar molecule overall. No one wins this tug-of-war. Okay. And number 19. Determine if the following molecules are polar or nonpolar. We're going to have to draw them. So we have carbon tetrafluoride, CF4, we have F, wedge F, wedge F. Definitely nonpolar because it's symmetrical. Water. Okay, hydrogens, and we've got lone pairs, and of course these hydrogens are out and in. This is totally polar. Oxygen very strong compared to hydrogen, and not symmetrical. Sulfur dioxide. Sulfur dioxide is a fun one. This is going to be an expanded valence sulfur dioxide, so we're going to have like this and like this. Oh boy, I may have to look this one up because the sulfur would still have lone pairs, yes? Am I going crazy? Maybe he has one lone pair? Oh, I miscounted my electrons. How about that? Alright, because this is a tricky one, I'll do it with you. Sulfur dioxide looks like so. We had sulfur, 6 electrons, oxygen with this many, 6 also. Now, in order for sulfur to bond, he's going to have to bump some of his electrons into a higher orbital. So he's going to have 4 free electrons in order to bond with these 2 oxygens, leaving him with a lone pair left over. So when you bond them, you get sulfur with a lone pair, which is going to take those oxygens and bend them. So this is a bent molecule, which will make it polar. It's not as bent as water was, so if we go back up to water, actually, yeah, it's technically bent. If that lone pair here was a molecule, it would look like a trigonal planar molecule. But because it's a lone pair, it's not. This is going to be more bent, because it's got 2 lone pairs pushing the hydrogens out of the way. This should only be a 120 degree separation, whereas this one I think is like a 104. Okay, going on. Phosphorus Pentachloride. Oh boy. Phosphorus with 5 chlorines. Alright. Chlorine, 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 wedge back, wedge forward. So these chlorines, 1, 2, 3, those would look like a trigonal planar piece. And then we stick the other chlorine on top and bottom. So when you have all 5 like this, you have a trigonal bipyramid, or trigonal bipyramidal shape. And because it's symmetrical, I mean, the trigonal planar part is symmetrical, and the chlorine on top and bottom are like a linear. This is like a combination of linear and trigonal planar. Everything's symmetrical. So this is going to be a non-polar molecule. There's no lone pairs in the central atom to worry about. Okay. And, well, let's see what else we got. Oh, hydrogen sulfide. This is easy. Sulfur, going to be a hydrogen here. Hydrogen here. This is bent. Definitely polar. Although not as polar as you might think, because sulfur is not that electronegative. But still weakly polar. Alright, almost done. So you've got 20, 21, 22, all the way down to 28. Yeah, this is a long one. Go attempt the end of this series, and then come back to the video. Alright, number 20. Dipole moment. I dropped this vocab term a couple sections of the video ago. Dipole moment is just how we measure how polar a molecule is. So they're showing 3 molecules. They've got the ammonia molecule. Here it is, NH. Let me redraw that. H, wedge, wedge. Okay. 1.42. Then we have N, Cl, 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 and then we have N, F, other wedge F, F. Okay. Polarity of a molecule can be quantified as the dipole moment. The dipole moment is either found indirectly or directly calculated, or calculated theoretically. So dipole moment is a made-up term for convenience. It helps describe things that go on. Measured in dBis. What is the abbreviation? Well, these said capital D for dBi. 0.6, make sure I have all the numbers here, 0.23. Which molecule is the most polar according to the dipole moments given? Well, according to them, 1.42 is the big one. There you go. Alright, number 21. Discuss the dipole moment values, propose some possible explanations for the changes in the dipole moments between the three molecules. In particular, note anything that seems unusual in the data. 1.42 for NH3, 0.6 for NCl, and 0.23 for NF. So the trend seems to be that as we go from hydrogen to chlorine to fluorine, we are getting a smaller dipole moment. And if we look at the periodic table, going from hydrogen to chlorine to fluorine, we're going left to right, and then also bottom, well, with the exception of hydrogen, fluorine is up the top. Fluorine is the most electronegative of the three of them. So going from hydrogen to fluorine, we're getting higher in electronegativity. The dipole moment is getting smaller. And the dipole moment is actually measuring the change, or the difference, between one atom and the other. In other words, this dipole moment is the difference between that hydrogen and that nitrogen, more or less, or the sum of those three hydrogens and that nitrogen, because they're pulling in one direction. So the dipole moment getting smaller must mean that as we get from hydrogen to chlorine to fluorine, we are having a smaller difference. In other words, nitrogen must be a strongly electronegative atom, which you would expect it to be. So nitrogen is strong, and then as the peripheral atoms get stronger, the difference between nitrogen and those peripheral atoms gets smaller. In other words, they get closer in electronegativity. Or, unless nitrogen is weaker than hydrogen, which is also possible. No, that's not possible. Is it? No, I'm not going to go with that. Okay. 22. The dipole moment of a bond or molecule is often represented with an arrow that points toward the more negative side of the bond. Negative meaning the stronger side of the bond, the more electronegative side. Determine which bonds in Model 2 are polar bonds using a table of electronegativity values. A large difference in electronegativity is characteristic of a polar bond. So the most polar bond is going to be between the nitrogen and the hydrogen, I believe, based on this. So let's find our table of electronegativities. Just to make sure, hydrogen is a 2.1. Nitrogen is a 3. Okay, I was at least right on that. Then we should have nitrogen and chlorine. Nitrogen, again, is always going to be 3. Chlorine is also 3. Huh. And lastly, we have nitrogen and fluorine. Nitrogen is 3. Fluorine is 4. Okay. Well, this actually paints an interesting picture. At least I find it interesting. Hopefully you do too. A large difference in electronegativity is characteristic of a polar bond. Which bonds are polar? The biggest difference is here, 3 and 4. That's a polar bond. The next biggest difference is here, 3 and 2.1. That's a polar bond. But this is not. Nitrogen and chlorine is very nonpolar. that bond anyway. Okay, so that's A. Polar, nonpolar, polar. Then B, for any bond that is significantly polar, draw an arrow to show the direction. Well, who wins here? Well, the 4 is a stronger electronegativity, so it wins. It pulls that direction. But up here, the 3 is stronger. It pulls that direction. In the nitrogen chlorine, there is no polarity. Okay, moving on, 23. The lone pair in a molecule also provides a dipole. Draw an arrow that points away from the center atom for any lone pairs. Okay. So if I go back up to my molecules here, no, yeah, I guess I have to. So if I go up to my molecules here, the lone pair is here, so there's always going to be an arrow pointing in the direction of the lone pair. Gotcha. So that's 23. Go on to 24. Consider the arrows you've drawn. Explain why NH3 is the most polar of the 3 molecules. Ah, now we should be getting somewhere. So going up to NH3 and considering, I'm gonna draw these arrows as well. So don't forget, I had an arrow pointing in the direction from H to N and an arrow from N to F. So now I get up here, and the H to N, remember N being stronger than H, the arrows point this way, and then up. In the Cl, there are no extra arrows, because remember NCl was not polar, they both have the same electronegativity, but here the fluorines are pulling this way. And the lone pair pulls up. Okay. Considering these arrows, why NH3 most polar? Well, look at it. Okay? All the arrows are pointing that way, up towards the top. Whereas if I come down here, I have 3 arrows going away, but 1 arrow going up. So they're going in opposite directions. From the fluorine is pulling opposite of the lone pair. So that makes sense. Now, number 26. The phosphorus trifluoride is dipole of 1.03. Compare this to nitrogen and propose a reason for the larger dipole. Okay, let's do that. Phosphorus trifluoride, fluorine, wedge, anti-wedge. There. So the fluorine are still stronger than phosphorus, and they will pull this way. Remember, phosphorus is below nitrogen. Phosphorus should have less electronegativity than nitrogen. So the fluorine arrows should be bigger, because fluorine is still really strong, and he's pulling on somebody weaker than nitrogen. So he should create a bigger dipole than phosphorus does. A bigger difference in the tug of war. There might be a lone pair arrow, but again, phosphorus is weak, or weaker than nitrogen. 27. Almost done, guys. 27. Rank the following molecules in order of polarity from least to most. Use arrows. Okay. They're all variations of this. What we're going to call a vinyl molecule, which is a carbon-carbon double bond. Okay. The least polar of all of these should be the one that has only hydrogens, because hydrogens and carbons are very close in electronegativity. If I look them up on this table, hydrogen 2.1, carbon 2.5, the difference is so small. So we will assume that this molecule is completely symmetrical, so even if one of these bonds had a little polarity to it, actually it would be the other direction. Even if one of these bonds had some polarity, which they do, they all cancel out because they're all pulling in a symmetrical fashion. Alright, so let's get rid of this. Now the next one that I'm going to draw will also be symmetrical. but it has slightly more polar bonds to it because there were chlorines attached. So the first one was all hydrogens. This would be this one is going to be trans vinyl chloride, whereas the first one was just a vinyl group. Completely, like, this cancels with this, and this cancels with that. So it's still nonpolar. In fact, you might go as far to say this is just as nonpolar as the one before it. Although most people consider carbon-hydrogen bonds just to be less polar. So, okay, so we got that. Then we have the third one here. Looks like we have an extra Cl over here. I'm going to go ahead and make a judgment call and say that the third one will actually be the one that's got the hydrogens up here, and it'll pull polarity down this direction. No, I'm second guessing myself. Let's go back. It's not going to let me erase that. Fun. So, we'll say chlorine, 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 hydrogen is the next up in polarity, because these guys cancel each other out, and you have one leftover chlorine pulling and creating a dipole in this direction versus this arrow here, which is going in towards the carbon, because carbon is stronger than hydrogen. And then lastly, you should have this one, where you've got chlorine. Oh, nope. Nope. No, that's a hydrogen, hydrogen, chlorine, chlorine, and you have in like this and in like this, so there's definitely a downward polarity to it. A lot of down arrows. Okay, that's 27. And now the last one. Comparing molecules in terms of who has got the largest dipole moment. Of course. Who wouldn't? Carbon and sulfur versus sulfur and oxygen. Well, one of them's bent and one of them's symmetrical. This guy here has the larger dipole moment. Definitely. Then we have water. I can totally draw today. This is why you shouldn't record these videos late at night. And you have oxygen difluoride. I would say water is going to have the stronger dipole moment because oxygen and fluorine are very close in electronegativity. Oxygen is like 3.5 and fluorine is like 4, whereas here hydrogen is only like 2.1, so it's a bigger difference. But they're both the same shape. And lastly, carbon tetrafluoride. It's a wedge. It's another wedge. It's a terrible drawing, don't judge me. And sulfur tetrafluoride. That's a little better. Oh, excuse me, I've drawn sulfur tetrafluoride improperly. Sulfur tetrafluoride. Carbon had 4 valence electrons, but sulfur has 6, so you'll get sulfur tetrafluoride with a lone pair left over. And then so this is going to be seesaw, isn't it? I guess you might have a square planar molecule if you wanted it. But I think this is typically considered seesaw. So yeah, I'm going to say this has the higher dipole moment right there. Just because he's got no symmetry. or doesn't have no symmetry, but has less symmetry than this, which is all symmetry. Okay, I hope you survived that. That was one heck of a POGIL. And we'll definitely talk about it more after the lab tomorrow and then Friday. I'm going to talk more on Friday. Okay? Get some sleep.